Okay, good afternoon, everyone. Thanks for coming this afternoon session. So I realized today is Lens Day because we had Massimo Inguscio, we had Claudio Lenz, and now we have Tino also from Lens talking about tests of gravitational physics with atomic sensors. Thank you very much for doing this very long trip here. And yeah, we're here to hear you.
Yeah, so first of all, I would like to thank the organizers for bringing me here. This is my first time, John Carlos. I'm very happy that I could have this chance. And I'm enjoying the meeting. I hope also I will contribute to the success of this meeting. So, okay, the topic of my talk is how we can test gravitational physics using atomic quantum sensors. And of course, as we know, this is also, this meeting also a tribute to Dan Kleppner. And I don't have the same experience that Claudio and Vanderlei had of interacting with this exceptional person, but there were chances where I could spend some time talking to him, and it was always very nice to talk with such a nice person and such a good physicist. And one case was certainly the Varenna Summer School on the Bose-Einstein condensation in 1998. And but also, thinking of that, I found this, in 2017, I was invited to give a colloquium, a Harvard MIT colloquium. And so then I could visit the labs, and I was invited for lunch by Dan Kleppner and Dave Pritchard. And this was really an experience. I guess the food was good, but I can't remember what I was eating because it was 1 hour full immersion in physics, in deep questions. They looked like, you know, two old friends asking questions to each other, and when they didn't know the answer, they asked me. And so just like a student at an examinations, I know what I guess. Yeah. So this was, for sure you know the answer. Well, maybe. And this was real physics, you know, with the back on the envelope calculations to check the numbers, something that I remember. Anyway, so as I said, I will tell you how to use atomic sensors to investigate gravity. Atomic sensors essentially means cold atom samples, so I'm not going through laser cooling. We heard already something about that. We are talking about samples with temperatures in the microkelvin or hundreds of nanokelvin temperatures. And as we heard already, in many applications, it is important not only to have cold samples, but also confined samples. So being able to trapping the atoms. For example, using what is called the magneto-optical trap, a combination of magnetic fields and light. And so here, for example, you can see this is a video in our lab, and the flash that you see appearing is a magneto-optical trap of strontium atoms. The resonance light that it used to cool the atoms is 461 nanometers blue light. And in fact, in this apparatus, we use also the Zeeman's Lohr system. That is the one that Bill Phillips was inventing and showing. When you cool the atoms and you confine them to have a high enough density, you can reach the conditions for degeneracy. And in the case of atoms that have a bosonic nature, then you can achieve the Bose-Einstein condensation. as we heard already in the talk by Bill Phillips. Okay, here also for the students, I remind what is a boson. A boson is, in the case of an atom, so a boson is a particle that has this feature, such that if you have two of these bosons, two of these atoms, and you exchange the labels of two atoms, then the wave function, the overall wave function must not change the sign. And so for an atom, what is a boson? A boson is an atom that has an even number of electrons, protons, and neutrons. So this is something that always, for me, was a little bit surprising, that if you take, as Massimo Inguscio was telling this morning, you take potassium, an atom of the atomic species potassium, and then you just add or subtract one neutron, and one neutron doesn't change anything. The nucleus is about the same, the chemical properties are the same, so really you're changing something. And then the Bose-Einstein condensation, for example, does not happen, actually. It becomes a fermion and it has the opposite characteristic. This is something to me always a little bit intriguing. There is a theorem connecting spin and statistical properties, but this is also something that has some open questions. Anyway, if you cool, you can reach the Bose-Einstein condensation, as was shown first by Eric Cornell, Carl Weimann, and Wolfgang Ketterle. And as we heard, all this was strongly influenced and allowed by the important contribution by Dan Kleppner, showing the importance and the possibilities of confining the atoms. He was choosing hydrogen, but the method was the same that then was used for the alkali atoms, and then the evaporative cooling, and eventually also for hydrogen, which is a difficult case, it turned out, you can reach Bose-Einstein condensation. In terms of tools that we have to manipulate the atoms, we don't have only the force exerted by the light on the atoms, but also we can use what is called the dipole force, or the effect of light shift, such that if you have, for example, a standing wave or a two-dimensional pattern or three-dimensional pattern, you can confine the atoms depending on the frequency of the light. But anyway, you can form very regular patterns of atoms, either as a series of disks or tubes or points. And so you can understand that this becomes an important tool for simulations, for example, of solid state or condensed matter systems. And one simple example, but I think very interesting, is what is called block oscillations. We know that if you take a crystal, a material, you apply a potential difference, there will be a current, the electron will flow according to the Ohm's law. But if, as Bloch did in the 1929 paper, you take the quantum mechanical problem, a particle in a regular potential, periodic potential under the effect of a force, what Bloch found is that there is no flow, there would be no current in such a crystal, but just an oscillation, a regular evolution, such that essentially the Bloch law, Ohm's law would not be possible. And this is because it's a quantum effect, but it is valid only in a perfect crystal. And we know that real crystals are never perfect. There are imperfections, dislocations, such that this regular oscillation is broken, and then the electrons can flow. And since there are no perfect crystals in nature, this effect had never been observed in a real crystal, and it was first observed by Christoph Salomon in 1996, published in 1996, but for a very short time, because then this coherence effect was lost. And what we found is that using strontium atoms, in particular strontium-88, which is an atom which has special features, it is it has a very small sensitivity to perturbations by magnetic field collisions. It's almost an ideal particle. And we found that we can observe these block oscillations, you see, for a very long time, up to almost 20 seconds. So this is interesting by itself as a quantum phenomenon, but also the frequency of this oscillation, if you make the calculation, you find that depends on the mass of the atoms, the wavelength of the light that you are using to produce the standing wave, Planck constant, and then gravity acceleration. So this is a gravimeter that works in a few microns. The size is just, you just need to fill a few of these wells of the lattice to observe this effect. This is one application of what is called optical lattices, but also for the optical clocks that we already heard about, and I will also say something about that. As was said, that to observe with high precision an effect, you must keep the atoms there. And one way, for example, in the case of optical clocks, is to keep them using an optical lattice. Okay, so this is a general introduction to the tools that we are using for the scope that I said. And let's go a little bit more in detail to the way these atomic sensors work. And the main example I will be telling you about is atom interferometers. In an atom interferometer, you have the atoms essentially are split. The wave function describing the atoms is split in two parts that propagate along different paths, and then they are recombined. And then if you detect at the output ports of this interferometer, you can observe interference fringes. This you can explain also in terms of a dual wave particle duality of atoms in terms of the de Broglie wavelength. This is a little bit like if in a soccer player would kick the ball and send the ball along two different paths. As I showed in this picture, I asked ChatGPT to help me to make the picture, but it was very hard to convince ChatGPT to make the drawing of the two lines. So it really did not want to do that. Eventually it made it with this strange line, but I convinced it. But sorry? Yes, in case of destructive, this is a constructive interference, I guess. Sorry? Yes. In fact, the goalkeeper is somehow surprised. So this seems a little bit like a joke, but in fact, in this experiment in Stanford, they were able to separate the atomic wave function. Each atom was separated in two parts, separated by 50 centimeters. So it's really like sending the ball along the two paths. Of course, for a real ball, it will not work because it's a classical object. This is also another topic. But this is sometimes considered one of the paradoxes of quantum mechanics. But in fact, there is no paradox because quantum mechanics as a system, as a model, is working perfectly. And it's only our way of, the way we grow up and we see the world that does not allow us to easily conceive the idea that we can go through two different paths. And in fact, this is a quantum interference phenomenon in quantum mechanics and quantum physics. If you have a system that with an initial state and the final state, that the system can go from one state to the other with more than one path, then to compute the probability to go from the initial state to the final state, you must sum the amplitudes for the different paths and then take the square. And then you get this term that is at the origin of the interference. And if something is happening, this is the equivalent of the optical interferometer, not like the Michelson interferometer or the... if there is some effect that is affecting in a different way the two paths, then the interference effect is expected to change. And one example that is relevant to what I'm telling you is the effect of gravity on atoms. Atoms have a mass, so they are affected by gravity. And then depending if you have the atoms, for example, as we will see in a fountain, depending on the path that each part of the atom is following, the effect of gravity will change. And so we can anticipate that depending on the effect of gravity, the interference pattern will be modified. Of course, all of this works if there is no which path information. When I showed before the picture, and I said this is the wave function that is split into parts, there is a trick there. That is an experimental picture that was taken not in our lab in Hanover. You could never record a picture like that, because once you detect what is the real path, the interference figure disappears. So that was taken as a series of experiments. So to have the interferometer work, you must not have any which path information. So for example, you cannot excite the atoms and get fluorescence, because that would be a way to identify the path of the atoms. And so one method that has been quite successful for atom interferometry is based on Raman pulses. This is a two-photon process where the atoms go from one state to the other, and you can tune the frequency in a way that it is essentially negligible, the probability that the atom goes to the excited states and then emits a fluorescent photon. So you can treat this as a coherent process for a two-level system from A to B, but you are using optical photons. And so the momentum of the photon is not negligible compared to the momentum of the atoms. And so, as we know, in a system, two-level system interacting coherently with radiation, you can tune the duration and the amplitude of the interaction to have what is called the pi/2 pulse and pi pulse. So after a pi/2 pulse, if the atom is initially in the state A, after the pi/2 pulse, it will be in a superposition of A and B with equal amplitudes. And after pi pulse, it will go from A to B. This is what was shown already as the basis of the Ramsey method. The difference here is that we are using optical visible photons. And so when, for example, you have a pi/2 pulse, you are not only inducing a change in the internal state of the atom, as I said, going from A to a superposition of A and B, but you are also transferring momentum. So after a pi/2 pulse, essentially you have a beam splitter effect. The atom that initially is going in one direction is split in one part that goes on with the same direction, and another part that is going through another direction. Okay, so this is a beam splitter, while a pi pulse plays the role of a mirror, because the internal state changes and the direction of the atom changes also. And so by combining beam splitter and mirrors, you know that you can make an atom interferometer, like a Mach-Zehnder interferometer. And this is the basic idea of these atom interferometers. Now, if you compute the effect, the change in phase in the interference pattern induced by gravity acceleration G, you find a simple expression that is given by k. K is 2 pi over lambda, the wave vector of the light that you use to as beam splitter and mirrors, gravity acceleration, and then the square of the time between the pulses. And so from the knowledge of these quantities, you can extract the value of gravity acceleration. And what is interesting is that if you put numbers that are you will see are typical numbers for our experiments, so like 1 million of rubidium atoms, with 1 million atoms, if you are at the shot noise limit, the classical signal to noise limit would be 1000. And if you take the time between the pulses of the order of 100 milliseconds, you find that with this system, you can measure gravity with a relative precision of 1 part per billion per shot. These experiments, as you will see, very often are done in an atomic fountain. If you launch the atoms, it will take a fraction of a second to go up and down. So essentially, in 1 second, you can measure gravity with a precision of 1 part in 10 to the 9. And I don't know if also here, when you are at first year at the university, you make as a laboratory experiment the measurement of gravity acceleration with the pendulum. This is a classical. And so if you have done that, maybe you remember that it takes 1 afternoon measuring the oscillations to get maybe 3 digits, I don't know how many digits in precision. Here, in 1 second, you get the value of gravity acceleration with 9 digits. And in fact, this was already shown in 1999, this paper in 1999 by the group of Stephen Chu in Stanford. And as I will show, these are already the best gravimeters that you can, absolute gravimeters, because you are using the atomic as in clocks. So you can, if everything is done, if you are controlling systematics, what I told you now, to be precise, otherwise I will be reproached. The numbers I was given is in terms of sensitivity. Then you must control everything, all the possible systematics. And then as for the clocks, you can rely on the fact that all the atoms are the same. Anyway, systematics is a hard job. But if you do everything right, it's already shown that the best way to measure gravity acceleration at the moment is with these atom gravimeters, both in terms of, certainly in terms of accuracy. There are relative gravimeters that are the superconducting ones that are more sensitive, to be honest. Otherwise, I'm selling too much this system. Okay, when this paper came out, I was moving from Naples, where I was before, to Florence. And so since I had to start new experiments, essentially I proposed this experiment with the acronym MAGIA, that in Italian stands for Misura Accurata di G mediante interferometria atomica, accurate measurement of big G, Newtonian gravitational constant, using atom interferometry. And the idea was that we use such an atomic gravimeter, but instead of measuring the effect of the Earth, Earth gravity, we use some external source masses, some masses that produce a gravitational field, and by the knowledge of this mass distribution, using Newtonian expression, we can extract the value of the gravitational constant. Now you can say, oh, gravitational constant is an old story. Cavendish was already measuring it more than 200 years ago. Why still? In fact, the gravitational constant is still, I wouldn't say a mystery, but it is something, as we heard already, all the fundamental constants now we can measure. I mean, we as the physics community, we can measure with 9, 10 digits. The gravitational constant still has an uncertainty of part in 10 to the 4. And this is because when different laboratories measure the same quantity, they find values that are not in agreement with each other by big quantities. So they are inconsistent. And you know, when you have inconsistent data, you cannot make an average. You can make an average of consistent. So this is an unsolved problem in physics. And all the measurement had been done before using more or less Cavendish idea, so using macroscopic sensors. Our experiment is the first, and so far the only one, that has measured this fundamental constant using atoms. Then you can say microscopic particles, quantum particles. So it's somehow a unique, some unique features. And the idea, as I said, we were using we developed a fountain of rubidium atoms. Instead of having one sensor, we had two sensors simultaneously. So this is a gravity gradiometer, because as I will show, as it is shown here, the sensitivity is extremely high. And so if you had only one gravimeter, you would see also the students in the lab. So you want to subtract the change in G and only measure the effect of the source masses. And so using such the sensitivity that I told you before, and using like 500 kilogram of tungsten, so even 500 kilogram of tungsten at a few centimeter distance give you a very small effect compared to gravity, Earth gravity, about 10 to minus 7. But because of the sensitivity of the detector, you can integrate over 10,000 shots and then get, for example, the measurement of gravitational constant with a relative precision of 1 part in 10 to the 4. That was the goal of the MAGIA experiment. You know, when you are young, you are ready to you have no limits, more or less. And so this was the initial system that I had proposed. The vacuum I wanted made by titanium, because titanium has several special features in terms of expansion for vacuum. It's a good material. But it is very hard to machine. And so, since the Ferrari cars are made in titanium, I call titanium Bologna, where they make Ferraris not far from Florence, Imola, Bologna. So I called Ferrari and I got a quotation by Ferrari to build the vacuum system in titanium. And then I asked the INFN, which is the funding institution, the Nuclear Physics Institute, I asked directly the president of INFN 1 ton of gold, because gold is one of these materials with about 19 in terms of density compared to water, very homogeneous. In fact, many experiments for big G has been done not with 1 ton, but with a small golden. And I also got the approval by the president to buy 1 ton of gold. And then the local director refused. I said, I cannot take the responsibility to keep 1 ton of gold for some years in my institute. But so that would have been a very good investment, because then the price of gold, this was the, as I said, beginning of the end of the 90s, beginning, and now I don't buy gold every day, but I know that the price went up by a lot, so it would have been a good investment. Anyway, this was not possible, but still the apparatus was done in a very, with the best that we could do in terms of a laser system, optical fibers. The system was done in titanium as I wanted, but I got another company with about, 1/10 of the price compared to Ferrari. And then the masses were not in gold, but in tungsten, which has about the same density. But we had to spend a lot of time to have tungsten with a very good homogeneity. And this is an animation how the MAGIA experiment was working. As I said, we were launching 2 clouds of atoms and then sending the 3 pulses to produce the interferometer, detecting the output, and then moving the masses and repeating the experiment. And so the output was essentially this ellipse signal. These are what are called the Lissajous Again, you must have seen that in the lab when you put on the oscilloscope two sinusoids on the two axes. And so here the two sinusoids are the two outputs of the two interferometers, the upper and the lower. So we get an ellipse, and then when we change the mass's position, we modulate this ellipse. And from the changing shape of these ellipses, we can extract the value of the gravitational constant. This was the situation when we took the data. And here you can see these are the experimental ellipses and the values that we could extract as a function of the position of the source masses. And you can see that the sensitivity was just one that I showed you on paper, of the order of 10 to minus 9 G per square root of Hertz. Of course, we were taking advantage of the differential mode. We were subtracting a lot of common mode effects in this way. And this was published in Nature in this paper. And it is now when you take the CODATA, CODATA is the committee that gives the numbers for the physical constant. If you noticed when Bill Phillips was giving you the example of the distinguishable or indistinguishable, he had these two small cards, and these were the cards with all the values of it was written CODATA on it. Anyway, the CODATA value now for the gravitational constant takes into account also this lens 14, that is the value that we obtained. And there are now other labs that are working at, an experiment must be repeated to check that results are reasonable. And so now there are experiments, for example, in China, in Wuhan, in United States, at Northwestern University, and also a previous student of mine, Gabriele Rossi, now is building a new experiment in Florence. And for example, the experiment at Northwestern University is based on an idea that we had proposed using, in fact, the block oscillations detector instead of the Raman interferometer, and taking as the source mass what is can be an almost ideal source mass that is a silicon crystal. The problem is that the density is lower, you need to increase the sensitivity, but I think that this could be more or less the final scheme for the determination of the gravitational constant. And this idea we have pushed a little bit in the past, also in the direction of measuring gravity at very small distances, because all the experiments on gravity have been done for macroscopic distances. So it is interesting to probe possible models that predict that gravity at very small distances would deviate from the Newtonian law. And along this direction, there has been work that we have been doing to improve these kind of detectors for very small measurement of gravity at very small distances. And this is the result of an experiment that was published last year by the group of Holger Müller, where they essentially, this is a sort of MAGIE experiment, but instead of having 500 kilogram, a big source mass, it's a centimeter size mass. Of course, there are many details because then you have to increase the sensitivity by a lot. So I'm not going in details, but it is interesting that it was possible, based on the result of this experiment, to set upper limit to possible models for dark energy, and also for possible deviations, Yukawa-type deviations of gravity from Newtonian gravity. And there are very interesting prospects pushing the performance of these quantum sensors to investigate other aspects of gravity. Another kind of experiment where many labs are now involved is testing the Einstein equivalence principle that essentially goes back to the idea of Galileo Galilei, of dropping from the Pisa Tower two different materials and checking if they're falling, if they're touching the ground at the same time. Now, as far as we know, the experiment was not done by Galileo Galilei. This was a Gedanken experiment. But the idea is very important, and it is at the basis of general relativity. And as I was saying, there have been now several experiments with different atoms, and also testing different aspects of possible violations of the equivalence principle. And one important one we just heard this morning, testing the equivalence principle for matter and antimatter, that of course I consider very, very fascinating prospect. Of course, as Claudio said, there is a long way now to reach the sensitivity of the experiments that are done with, let's say, normal atoms, but you are really probing a crucial aspect of physics, several crucial aspects of physics in that way. One of the experiments that we have performed was done with strontium again. Strontium, as maybe you understood, is an atom that I like a lot, and not only myself. And we tested the equivalence principle for two different isotopes of strontium, strontium-88 and strontium-87. Essentially, we drop the two isotopes and we look for possible difference in gravity acceleration. And this is interesting because strontium-88 has no spin, no electron and no nuclear spin, while strontium-87 has a nuclear spin of 9/2. And strontium-88, as I said, is a boson, while when you take out one neutron and you get strontium-87, this is a fermion. So this experiment can be interpreted as a search of a possible coupling between spin and gravity, that is, in some models of gravity is present, and also checking if bosons and fermions. There are theoretical papers also predicting possible differences between the gravitational interaction for bosons and fermions. And as was said this morning by Massimo Inguscio, investigating properties of fermions in Florence is particularly interesting because Enrico Fermi was a professor in Florence when he wrote his paper on particles that don't have the bosonic nature, and that then they would have been called fermions. Okay, so this is all very fundamental, and but as I already said, these are not only important sensors and tools to test the fundamental aspects of nature, but also for applications in the field. So, for example, this is a transportable atomic gravimeter that we developed with the support of the Italian oil company that Massimo Inguscio was mentioning this morning. This was done now some years ago. And now a similar atomic gravimeter is running on the Etna volcano in Sicily. Because, you know, if a volcano is erupting, there is the magma is moving, and then the gravitational signal will change. And so you can, using this gravimeter, for example, you can probe the motion of magma and predict eruptions and things like this. Okay, I don't need to tell you much about the atomic clocks because we had already a very interesting and instructive talk. And it was already shown that with all the improvement of clocks based on microwave transitions, essentially cesium and rubidium, with all the improvements also taking advantage of the atomic fountain, at some point the optical clocks, the clocks based on optical transition instead of a microwave transition, they gained a lot in terms of accuracy. And so now they can be considered, in particular the ones based on strontium, but not only those, are potentially the best clocks at the moment. And this is to show that this is something, as I told you, strontium I chose as one of my favorite atoms since a long time. This is the first paper in 1992 where we investigated the intercombination line of strontium, proposing as a frequency reference. Here, if you can see, it's, the line width is 6 megahertz, and then working for 20 years, we got to the point of a line width of about 6 hertz. So it was 6 orders of magnitude in 20 years, which is typical in this kind of work. And now the performances of these clocks improved by a lot. And one important effect that can be investigated with precise clock is the effect of gravitation on time. Because a clock that is close to a massive body runs slower than a clock which is farther from the source. And if you put the numbers, if you approximate the general relativity prediction, and you consider the Earth, on the Earth, if you move by 1 meter, so if your clock is on the ground or you raise it by 1 meter, the ticking, the frequency of the clock will change by 1 part in 10 to the 16, which is a small number, but as we said, the precision of this system is extremely high. I guess these are the most precise tools that we have in physics. And so, for example, already in this paper, you can see that Dan Kleppner with Robert Vessot and Norman Ramsey were, in fact, studying the possibility of using clocks in space to measure this gravitational effect on time. And this is a very nice paper, of course, physics, which is analyzed in a very deep way. And again, this is very fundamental in physics. Of course, it depends on the tools. Very often, physics is nice, you can have nice ideas, but then you need the right tools to... And so these things became possible when first the microwave clocks and then the optical clocks reached a precision to be able to distinguish this small effect. But this is not only fundamental, but also very important for applications, because you may know that if in the GPS system is based on 24 satellites that are orbiting at 20,000 kilometers from the Earth, so this effect is very small for 1 meter, but if you have 20,000 kilometers, it becomes not so negligible. And in fact, if you will not correct the system, taking into account the general relativity effect in the GPS system, when we use our mobile phone and Google Maps and so on, this would be wrong by 10 kilometers per day. So already in our simple, let's say now simple mobile phone, we have to take care of this general relativity effect. Otherwise, we would go in another place. This is because of the large distance between the satellites and our mobile phone, let's say. But with these new optical clocks, as I said, the change in the ticking of the clocks is 10 to minus 16 per meter, if you raise by 1 meter the clock. But with the optical clocks, now we are reaching, generally speaking, 10 to minus 18 to 10 to minus 19. This means that you see this general relativity effect over 1 millimeter. And this is something, I think, it is a big problem in some sense, but also something new opportunity in physics. A problem because now you can no longer define the time easily. Because if you define the time here and then you move here, you have a different time. So this is something that I think is still an open problem. But on the other hand, it's a big opportunity to investigate. It's a new tool, investigating the change of time due to gravity. And again, with the advance of fundamental physics, you get new possibility also for applications. Because, for example, if you want to compare the geoid, the gravity potential in Europe and in America, how do you do that? And this is important for many applications. And so with these clocks, you can do that because you can measure the frequency on one side of the ocean and on the other. So, fundamental physics and important applications. How can we push the limits of sensitivity, thinking now mostly, again, to atom interferometers? As I said, the expression is quite simple. The change in phase depends on the wave vector, gravity, and the time between that defines the size of the interferometer. How can you measure the change in phase with a better resolution that I showed before? One possibility is to use the squeezed states. As I quickly said before, the limits, when I gave you the estimate of the sensitivity of the atom interferometers, I told you the sensitivity for 1 million atoms, the signal to noise is 1,000, because it goes for classical states, for uncorrelated atoms. Essentially, you have a Poissonian distribution, and so the signal to noise depends on the square root of the number of atoms. So if you have 1 million atoms, you can have a signal to noise of 1,000. But it can be shown that with special states, essentially entangling the atoms, in principle, you could go from 1 over square root of n to 1 over n. So instead of 1,000, you would go, in principle, to 1 million in sensitivity. And this is something that, for example, for optical interferometer, already now, since some years, the LIGO and Virgo detectors of gravitational waves are using entangled photons, no longer it's squeezed light. They are using squeezed light rather than normal laser light. So we want to try and do the same now for atoms. And this is already happening. This is a paper that just appeared last week in Physical Regulators, where the group of Juni in Boulder, Colorado, showed that the clock precision can be improved for now by a little bit, but reaching a limit of 10 to minus 18 using one of these squeezed states, what are called spin squeezed states for the atoms. And we are working in my group now to show a similar improvement, but in an atom interferometer using squeezed states for atoms. And this is an idea that we published some years ago, but all these things take long to go from the idea to the implementation, and very long to find a real advantage compared to a system based on a classical source. Anyway, this is a prospect to increase, to improve the sensitivity using entangled states. The other tool is to increase the K, and so this goes in the direction of what is called large momentum transfer. That usually implies very difficult schemes. We performed a relatively simple experiment. Usually all these interferometers with rubidium and cesium use the resonance light, the first excited state, the transition going to the first excited state. But we performed this experiment, we developed the system to use a higher excited state. So higher frequency means higher K, essentially is a factor of 2, just changing the wavelength of the light. And you can see here that the ellipse, the blue and the red ellipse, compared to the black one is the one with the classical 780 nanometer transition. And these others are using this blue transition. So we gain a factor of 2. There is a larger change in phase. So this is something new and could have some prospect in the future. And then the last handle that we have is the interrogation time. And for that, you want to have a longer flight for the atoms. And so there are, in different laboratories, there have been developments to have longer and longer fountains. In Stanford, 10 meters, in Wuhan, 12 meters, and in Florence, now we are developing these 6-meter fountains. But then this is just to show the feasibility, and then there are prospects, for example, this is going on in the United States, to have a 100-meter interferometer, atomic fountain. And for example, there are prospects maybe to have such an interferometer at CERN. There has been already a study to show that that can be done at CERN. And this become, compared to the usual laboratory experiment, this become a little bit larger adventures, and so they require bigger teams, bigger groups, and so there is a community which is growing towards these terrestrial, very long baseline atom interferometers, aiming to fountains of the order of 1 kilometer, because with those, that kind of interferometer, for example, you could have a possible detector of gravitational waves for lower frequency compared to the optical LIGO and Virgo detectors. And then eventually, if you want very long time of interrogation, you must go to space. And this is something that we have proposed now for some years. You can find some detail in this paper. Of course, this is a long-term adventure, but if it could allow you to investigate, to observe gravitational waves in the low frequency range, search for dark matter, measure the gravitational redshift with a very high precision, and testing other aspects of gravitational physics. This is based, the basic idea is not to use a Raman transition, but a single photon transition. In fact, strontium would be the best candidate, and the beam splitter and the mirrors would be realized using the optical, the same transition that is used for the optical clock. And we showed in this work that this idea, at least on the small scale, works. So this is a sort of very small pathfinder of a future interferometer in space. And again, on ground, you need a large community and a lot of funding. In space, you need a much larger community and really substantial funding. So also for this, we are putting together a community of scientists that are interested in the experimental and theoretical aspects, more technological for developing these systems for space. And there is a roadmap related to these cold atom sensors in space. Just this year, it was mentioned the Crystal Salomon mission was launched to the International Space Station after about 30 years of development. And then there are these prospects at the end to maybe in 2045 to launch this the combination of optical clocks and atom interferometers on a satellite for probing fundamental aspects of gravity. And of course, given the time that are shown here, it is important that young people, young scientists get involved, because some of us will be retired at that time. And so in that sense, I would like also to acknowledge the work of the collaborators that performed the work that I showed you today. And thank you for your attention.
Thank you very much. Questions? Yes, I start here.
Hi, Guilherme, very nice talk. On your measurement, the MAGIA measurement, you have to measure precisely the distance between the masses and where you are launching the atoms? How is that done? Is that a major source of uncertainty, or?
Yes. So this was one important point. And in that experiment, so there are two aspects in your question. One is the gradient. So the experiment was designed to reach 1 part in 10 to the 4. So for example, we didn't bring the masses as close as we could have done, just because otherwise we would have had a gradient too large than to determine the mass, the atom position. Then the density of tungsten is high enough that in a small region we can compensate the Earth gravitational gradient. So the answer is yes, that is a problem, especially because it's not uniform gravity. Both the masses and the Earth have a gradient, and then a small change in the position of the atoms would affect. But at the level of 10 to minus 4, the way we designed the experiment, the gradient induced by the source masses compensates the gradient of the Earth. So in the position we were taking the measurement, we were less sensitive than we could have been. And in fact, the experiment of Gabriele Rossi, the next version, one of the crucial points is just to, it will have big masses to cancel the gradient and being less sensitive to this point. Of course, then all the thing was done in a very, all the mechanical parts were very micrometer precision.
Tino, very nice. Tell me, just a kind of, like a cosmological question. If we have a network of clocks with high precision, because you have already a network of people working in this determination of Earth, can we imagine a way to measure gravitational waves when we put all this together? Because then I will see tiny variations, but I can see that evolving, right? You think this is a possibility?
I think so. This is something that I have in mind somehow, but at this level, not with the more precise than you just said. I think the idea is good.
With one, you can't.
No.
But with a series of clocks that they are synchronized somehow, we should be able to, because they say that we are receiving gravitational wave all the time, right?
Yes.
So we should be able to analyze the statistics of these and things that the interferometer are not doing.
The scheme that I showed at the end, that I said this is an interferometer with the clock transition, is exactly the same. You have two clocks, strontium clocks, that are separated by a few kilometers. The problem is how to compare. So I think the idea is good, because you have the effect.
No, come on, we can't compare the clocks. We can make the clocks to operate together. And we can make sure that they find the deviation in the right sequence. So we can detect.
And then maybe it's hard to, I think it's difficult to make a direct comparison of the clocks, but you can have some post-processing and then...
Yeah, because then the whole Earth is a good detector for gravitational waves.
Yes.
Okay.
People are also thinking of the moon.
That's too far. We need to do things on the surface. We can fix it.
So I think it's a good idea. To go to details, it takes some more.
Okay,
thinking.
yeah, of course.
But I think the idea, is good.
All right, thank you.
The moon has less earthquakes, much less earthquakes, so it could be a good, but it's difficult to make. Yes. No, but I. But that's space, and space takes time, as I said. Also in my life, I've been proposing, as Claudio was quick, I proposed this 30 years ago, and still While the idea of having on the Earth, because there will be optical, there are and there will be more and more optical clocks. And so if you find a way to analyze in the right way the... Yes, then waiting to send, I agree, yes.
Thanks for the very interesting talk, very instructive. We could see the evolution of all those areas. I have a question about this, when you told us about squeezing. So I know that squeezing, in some cases, it really helped, for example, for detection of gravitational waves. After, I have the impression sometimes that squeezing, in theory, can be very nice. In practice, sometimes it's not worth the effort. So I would want you to comment a little more on this effort you are taking or intend to take. So how much you think you win? Is it worthwhile? What are the strategies?
This is, I think, a general statement, because for light, I remember when people started to develop this the squeeze light towards the gravitational wave detector. I think I was still a student, and in Virgo and LIGO it started working, a couple of years ago. So it takes a long time. Eventually, in that case, they gained, now I don't remember, 3 dB or 4 dB, but it took, 30, 40 years to go to. What you are saying about, is it worth? So it is worth if you want to see what you can do in general. The critical point at this moment for atoms is that, for example, what I showed before for the clocks by the group of Juni is one of the first demonstrations of a real improvement that you get using squeeze states. While there are many papers already showing that you improve the system, but with a tricky aspect that you take a system which is not working at the state of the art, and then you improve it. So is what you are saying. You show that you can improve, but taking something which is not working so well. Sorry? The internal state is what they call the spin squeezing, is the two-state. In the case of the interferometer, it's still to be shown, because all what has been done so far with this warning that very often is not really improving, but showing the potential on something, it has not been done with the real interferometer, where you have external states. So this method that we proposed, if it were, also other labs now, they are trying to implement it. It has not been shown yet for a real interferometer that you can improve the real sensitivity using entangled states, squeeze states. Maybe it will take 40 years also in that case, we will see. Usually with atoms you go faster in the development, but...
Hi. Thank you for the very nice talk. And just commenting about what Banhato mentioned, so your idea is actually being, people use pulsars to actually measure that. So your idea would be basically doing, instead of pulsars, bringing the clocks on to Earth, right? But they used pulsars to actually measure. They are trying, at least. I don't. I'm not aware of. Yeah. No, it's certainly not a bad idea, but because they are already using that, but for using pulsars as clocks. Yeah. Yeah, I know. Okay. And I was a little intrigued by your comment that there are some inconsistencies with the measurement of the Newton's gravitational constant. So I'm a little intrigued because of that, because of the following. From the fundamental point of view, G is basically a conversion constant. So a conversion factor. So even though we call it Newton's constant, Newton himself never actually introduced it. It was like introduced, I believe, in the late 19th century, right? So Newton understood that there's no point in actually defining that constant, because you have, in classical physics, there's no way to measure mass as absolutely. You always measure like relative
combination.
to, yeah.
GM or...
Yeah, exactly. You always measure GM. So my question is, how can you be sure that the precision of the measurement of the masses, the source masses for the gravity, are under control to actually say that the problem is with the measurement of the G's? I don't know if I was...
Yeah. I think this is a difficult, interesting, important question. One aspect, just inspired by your measuring BG, one problem is that BG, as far in our now understanding of physics, is not connected to anything else. So some people get some psychological problem. Some people invested their scientific life to measure BG, and then you have no reference. They told me that they wake up in the night, oh, maybe I forgot to do something, because you have no way to check. You just have to make sure that you controlled all the systematics in the best way. And this is also a little bit of a problem, because the only check comes, I would say, from the consistency. If you measure the same quantity in different ways, and you find the consistency, then you can have some indication that the situation is under control. But at the present model, you don't know. It can be a stupid mistake or something. There are papers showing that there would be some reason, fundamental reason to. So this is one aspect about measuring it. About the mass, you're right. We did it as well. All the mass characterization took a long time for us, and the measurement was done by our meteorological institute, taking the mass. But for mass, I think we are also facing the situation that while most of the other quantities now are defined in terms of quantum.
Exactly, yeah.
For mass, for example, our measurement was still, eventually as a reference, was still the Sèvres. So you're right. Technically we did it right at the level we can do.
I understand.
So
Okay.
meteorological, the fundamental aspect, you're right, because this constant as a, I think it goes back to the problem that gravity in our present understanding of physics is out of, and so it goes together. Gravitation constant and mass are the problem of gravity.
Mass, right? So it's not really possible, at least using classical physics, it's not really possible. When I mean classical physics, I mean considering that the source of gravity is classical, right? So of course the experiment is not classical because you are using quantum interference to measure the effect of gravity. But your source is still classic, right? And there's no way to actually separate M from the big G. So you always measure
from space, what you know from, as you said, from the from cosmos, we only know G times M.
Actually, I want to understand this discussion better because I was confused about this idea of G and M, like G being a kind of depending on M, because so for the mass, if you assume equivalence principle, the mass, the inertial mass can be independently measured. No, for example, you could get the ratio between the electric charge and the mass. So I would have a way of measuring the inertial mass, and from that I would need to fix the value of G. I understand that big G is just related to the gravitational mass, but inertial mass is related to lots of different measurements. So I didn't understand this. I understand that it's difficult to measure mass. I think it's one of the things that you measure with less precision, so I understand that it's difficult to calibrate, but you would need to measure inertial mass, assume equivalence principle, and then you would go to measure big G.
In our experiment, one special feature also, of our experiment is also that there is this aspect that you are saying, because usually the big G experiments are done with the torsion balance or pendulum. In our case, the probe is falling. So also the equivalence principle, the equivalence of inertial and gravitational mass plays a role in our experiment, more than in others, because the atoms are also falling, are not... what I was saying about the connection of big G and M, I think it's particularly true for, because we could say, okay, we have all the universe that is giving us a test about big G, but you don't know the mass of the planets, and you cannot separate big G from the mass. In the lab, of course, you can at least measure them, but then like, yes. Yeah. Yes. Should be done. It's a question of numbers. It's difficult to go from atoms. Yeah. But there are many orders of magnitude. That's it's a the the smallest mass, I think, is the one that I showed in the Holger Muller. It is a 1 centimeter size, where you can really measure the gravity produced by that source mass. So it's still a big. Yes.
Good, great. I think we have time during the break for further discussions. Before we thank Guglielmo again, two reminders. After a Milson talk, we have, if you are interested in seeing the labs, we will leave from here to do a lab tour. And tonight at 6, we'll have a public lecture, this in Portuguese, but about quantum mechanics from Vanderlei here also. So we are all invited. So thank you again for the wonderful talk.
Well, hello. We go to the last presentation, the last talk of the afternoon. And Amilson will talk about ions. And so, Amilson, it's up to you now.
Thanks, Daniel, for the introduction. So today I will talk about these trapped ions. This system is the system that we started building here in this institute. Unfortunately, we are now starting to put together all these pieces, and probably in near future we have some results to show. But so far I will talk in general about this system. Okay, so the idea, of course, is when you start talking about trapped ions, the first thing that appears in our mind is this is a quantum computer. And this is, of course, some of the idea or what motivate people to spend a lot of time working on this, improving these kind of systems. And why? Of course, there are different ways to say why you need a quantum computer, and theoreticians will know better than me why you need this. And there's, of course, different answers. These days, there are kind of problems, usually the problems that involve a lot of different parameters. Then you might wonder if you can solve faster by using classical quantum computers, and also if you really can solve some problems. And I just put in a different way here that if you wonder if you have a classical or a problem that you cannot solve now, if you increase the speed of classical computers, if you will be able to solve the same problem in near future. And I show here one of the plots that I just got from the internet in general. So here's the speed of your CPUs as a function of the years. And you probably will realize this in practice, that if you wait 1 or 2 years to get a new computer, you don't get a much faster computer after 2 or 3 years. And there are, of course, technical reasons why this is not happening. But the thing is that over the recent years, there's not much progress in terms of the speed. And that's maybe one of ways to probably solve this is go to these quantum computers. And the reason is that we can use probably a property of this quantum mechanics, that's the superposition of states. So here, what I show you, this is that this in a very simple way that you can represent. In a classical computer, every operation you do is binary, so you have zeros and ones, and this is most, of course, for the students. I'm not talking to the experts, of course. But the basic idea is that instead of this binary representation, you can take a qubit, that's a quantum version of the bit, and you can put in a superposition of 2 states, which we call here 0 and 1. And the idea is that you can have any combination of zeros and or any combination of these 2 different values, you can put in the system in a superposition. So then you can think about, of course, oh, now I have one bit that has very different values or infinite values, and I have probably one bit can take any different value, so I can replace this quantum bit by many, many different classical bits. And in reality, that's not completely true, because the way we measure them is what people have already talked about. This is the collapse of the wave function. So once you measure, you can only get one value. So then, even if the system in a superposition of these 2 states, once you measure, you only get or 0 or 1. You don't get this 50% or 70%, whatever, unless you measure multiple times. And this is what I show here in this plot here. So this is basically the probability, the excitation probability of that you can put the system in this superposition. So basically what you see here is the probability of measuring the state of this qubit as a function of the pulse. Basically, I will go in more details about this, but the idea is that you put a laser beam that is on resonance with these 2 states here, so you can bring the atom from the ground state to excited state. So basically, you flip from 0 to 1. And depending on the duration of this pulse here, which we call Rabi oscillation, so you can go from 0 to 1. So if you repeat your measurement in a pi pulse, you can put the atom in the excited state, so you have 0, from 0 to 1. If you put a pi over 2 poles, when you measure, you still get 0 or 1. But if you do this multiple times, then you will have like 50% of chance of get 0, 50% of chance getting 1. And this is what builds this kind of plot here. Then you say, then I go to a quantum computer, what system I can choose? And these days you can have different systems, different ways of working with quantum computers. So we have, for example, in my case, I choose trapped ions, but we have neutral atoms. There's a lot of advantages in one system or the other systems, but I will not tell you why you should not, or you should prefer one system on the other, but I will just say why trapped ions are good. So they are natural qubits, and this is what people say about atoms. So it doesn't matter the atom you choose. So if you go to Europe, Brazil, whatever, these atoms are identical. And this is not the same if you build a computer with superconducting qubits. So it depends. So it basically is artificial. So if you build something that's slightly different than the other, they behave different. So, and with ions, as the same of neutral atoms, they can be individually trapped, isolated. They have the longest coherence time of all these qubits, and they are identical, okay? But they have disadvantages. For example, and this is one of the reasons of these talks, it's very difficult to scale up. So you can build this system with few ions, you can go to many ions, but it's very difficult to control. On the other hand, for example, the superconducting qubits, you have a very high hype on this because you can build this system with very short period. For example, here is 2021 to 2023, and they increase from 100 qubits to 1,000 qubits. But it doesn't mean that you can use all of them. So I probably can say, or I don't know, theoreticians can say this better than me, but probably if you can control these 1,000 qubits, all at once, with all of them, with best control in the world, if you can do this with 1,000 qubits, you should be able to solve any kind of problem. So this is actually impressive, but in reality, that's not at all under control yet. So in this talk, I will talk about this system that we start to build in Brazil. But overall, how they can be trapped, how can be cooled, and the ways we cool them, and how you can, or what people are thinking about these days to scale up these systems. And the basic principle of trapping ions is very simple. This is actually not quite idea. Everything is classical here. The idea is that you first take a neutral atom, you ionize them, this ion, and then this is actually a charged particle. And the best way of interact with this charged particle is by using these electric fields. So the idea here is that you have this system here, is that the system that you can have analytical expression for the potential, for the ion's trajectory, and so on. And this, basically you apply radio frequency, and the idea is that you basically apply identical force in two directions. So you force the ion to be at the center, but at some moment you need to do this in all directions, otherwise you know that you cannot trap any charged particle by static force. So then you do variations of the electric potential in a very fast way, and that's the reason they call radio frequency traps. They operate more or less in megahertz. And then the idea is that at the end you can obtain an effective potential that we call pseudo-potential. And this, although this has analytical expression, is pretty bad actually for the optical access. So once you build this, you cannot see the ions basically at the center, or you have very poor optical access. So then this leads people to build different versions of these traps. And this is where the big companies becomes very important, because they spend a lot of time actually and money to build these beautiful versions. And here is the three-dimensional version. It's very similar to the ones we are building, is very similar to this one. And we have these other versions here that are surface traps. So this is not a three-dimensional trap, but they all have advantages and disadvantages. So without going in many details about this, but the idea is that once you put the ion there, they will look like as particles like this at the center, and you can manipulate them by using tiny focused laser beams. So you can individually manipulate each one of them. And with these ions here, you might wonder which atom has this structure that I'm presenting here. So when you choose one ion to trap, you can take the periodical table and decide which atom you can trap. And of course, these experiments these days are made for sometimes a particular reason, right? You design your experiment, you build, because one atom can be better than the other for some particular reason. So, but in all of these recent experiments, or most of them, they all look like this, in the sense of at least two requirements you need. So one of them, it's a very fast transition. I mean, like the ones that, for the students, once you put the atom in the excited state, it decays very fast. So this is one transition here that I put in blue. And also you need a very narrow transition, that the way that once you put the ion in the excited state, or once you transfer the atom to that state, it takes very, very long time to decay, right? So this is what people use, for example, for these, what we call clock transitions. So they use for, I would say atomic clock, but not optical clocks. And this is actually what gives you very good precision, this spectroscopy, and there's a lot of reason. So basically, you need these two transitions here. And the reason you need the blue one, it's very simple, because you need to cool them. And the other one is because you need very high fidelity in this spectroscopy and this, what we call gates for quantum computing. Then there is this question, for example, if you put the atom in the excited state, in some cases, in some atoms, it might decay in a few minutes. Other atoms is a few milliseconds. In some atoms are a few minutes. And then it stops interacting with your detector, for example, because once you put the atom there, unless it decays, you will not be able to do this transition anymore. And the idea here is that instead of looking if the atom is in the excited states of this, you look if the atom is not in the ground state here. And that's one of the reasons you need another transition, because the idea is that if you put this transition here, if you couple this with two lasers, so you have one possible transition here that takes very, very long time, but you have one transition here that is very fast, and this scatters many, many photons. And then what you see is this kind of plot here that people call the quantum jumps or the electron shelving technique. And the idea is that, as you can see, what you see in this plot here is how many photons you can get from this transition here, from the blue transition. And what you can see is that at some point you have very good countings, and in some moments you have almost no countings. And the reason is that if you have this transition here on, if the atom is here in the ground state, it can do this transition here. But you just need one transition to this excited state to stop seeing any scatter light, because once the ion is there, or the atom, whatever, it will not decay fast, and then you lose the counting. And this is what people use to probe the ions and to give these very good certainties, I would say, that you can measure the ion position or the ion state. And this is the reason, because if you count here how many counts you have compared to this situation where you don't have any counts, it's a huge difference. And then you can use this to say for sure you have the ion in that position. The other thing that is important, is very common in these kind of experiments, is the energies. So when you trap the ion there, you basically have, even before you interact with the lasers, So you have these two types of energies. So you have the internal state of the ion or the atom that brings the atom from the ground state to excited states. But in addition, you are trapping these, in the first approximation, you trap them in a harmonic potential. So this harmonic trap, that is your trap, creates these kind of energies that is the ones that you see in the quantum mechanics books. So this is a quantum harmonic oscillator. And for this, you can have here the discretized motional state of the particle. And this might happen. You can do these two types of transitions, okay? And this is very useful, actually. So the first transition that I just told you that you can use to count the ions, so to check if the ion is the excited state or in the ground state, is also used for Doppler cooling. And we have this twice explaining this in previous talks. Bill Phillips quickly shined on a slide about this. And the idea is this, the Doppler cooling is a very powerful tool that people use for getting bosons and condensate, for cooling ions and many different systems. They all more or less go through this situation here. So the idea is that if the atom is in a very high velocity, when you put the laser to interact with the ion, it sees a different frequency because it has a very large movement. And the idea is that if you put a laser beam that is slightly, with the frequency slightly below the transition, the resonant frequency, the ion will lose energy every time when it interacts with the laser beams. So then in principle, you can cool the atom, and there's a limit for that. And there's theoretical expression. In the first approximation, this is given almost for this expression here. Then you can see, for example, the powerful technique that brings you from room temperature, which is about Kelvin, to, in some case, milli-Kelvin or micro-Kelvin, depends on other details on the atom, for example. But this is actually brings you to milli-Kelvin. Then, if you can compute, for example, this harmonic oscillator, you have this energy level of the harmonic oscillation. So you have the occupation number, or the quantum number of this harmonic oscillator. Just after Doppler cooling, you have n about 10. What this means? That on average, you are not in the ground state of the harmonic oscillator, but you are already occupying the lowest states of the harmonic oscillator. Is this good for the experiments? And the reason is that if you look in the plot before, you are not in the ground state of the harmonic oscillator, that's for sure. But this is not actually what defines if you need to cool or not even longer this ion. And the reason is this: you need to take into account what we call lambdic regime, or the lambdic parameter. And this brings you additional information. And in simple words, what this means is that if you shine a laser beam on this atom, it of course will get some recoil energy, so exchange energy with the beam. And if this beam does not change too much the energy levels of the internal or the energy levels of this harmonic potential, then you are fine. Depending on the experiments, you will be able to tell that every time you start in the same condition. So this is actually what represents in this expression here, is the recoil energy compared to the energy of the separation between these energy levels. And this is actually tells you, for example, that even if you have n equals 10 just after Doppler cooling, you're not too bad, because this parameter here that should be much smaller than 1 now is about 0.2. So that means you have very low probability of using this laser, 674 for example, to excite another motional state of the harmonic oscillator. So then for many experiments this is fine. And of course, many of these experiments with trapped ions were done, many results were obtained with just laser cooling. But now if you need more, for example, for quantum computing, then this might not be enough. You need to start with the ground state. And then enters the motional state of the ion, how you can cool the motional state. So we start with more or less n equal 10. That means is even in this picture here, the ion will be occupying higher motional state of this ion. One technique that you can use is what we call sideband cooling. And I didn't put all the algebra here, but the idea is that now you need to make these energies here to interact with the laser beams, right? And then you do all the descriptions, and then you get 3 different situations. So depending on the laser frequency. So if you have a laser frequency that is resonant with the internal state of the ion, you just flip from 0 to 1, this your qubit, let's say. If you now have one, if you tune your laser beam by exactly this separation here, plus the separation of this harmonic oscillator, then you not only flip the internal state, but you actually move by 1 unit the internal motion of this ion. And the best, actually, version of this is when you tune your laser beam by this amount minus this separation here. And when this happens, if you apply your laser in this condition here, every time the ion goes from this side, from the ground state to excited states, it loses one of these n, or one quanta of energy. So it exchanges energy with the laser beam. So basically it loses energy. It loses motional state. And this is what is represented more or less in this picture here. But the idea is that this is basically given by the trap frequency. Just that. So by tuning your laser beam on the resonance, you can do one kind of transition. If you tune your laser beam on the resonance minus the trapping frequency, then you can force the ion every time to go to the ground state. And this is a very powerful tool to say I always start in the same system. It does not matter how many times I apply this, but if I say I applied 100 times, it will never go below 0, of course. And then what you see is this kind of plots here. So this is actually what a visual interpretation of these sidebands. So basically you scan your trap frequency here and you see how many photons this system absorbs. And if you put the laser on this frequency here, after, in this case here, 10 times that the ion goes from the 0 to the excited state, it loses 1 photon. So after 10 interaction only, you put the ion in the ground state. And where it goes, it stays. So it does not go anymore below 0, below the fundamental state. And this, of course, can tell you that you can always start your experiment in the same position. And this is actually what you show in this plot here, that is how many photons is scattered by this transition versus the detuning. So the higher peaks here are the Doppler cooling. So you already see that you have more photons in the blue transition just because this transition has better coefficients for the scattering. And after this, you almost don't have any atoms, I would say, scattering light. And then this is, of course, the ground state. And this is actually very important because this puts you or gives you the ability to set another qubit besides the one that is the ground state to excited state. So this is actually the sideband motions or the motional motion gives you another qubit. And this is actually what people use in the first demonstration of a logic gate. So for those who are not familiar, computation is because we do computation with gates. And the gates, you have many different gates, C0, Hadamard, and so on. And these are basic operations that you do. And this is one way of using this motional as a qubit and was being used in the first demonstration of this. When quantum computation started, it was first demonstrated by using this kind of system here. And this is actually the plot I think Celso showed in his presentation, the group that he collaborated in Stockholm. Once you reach the ground state, you just need to pulse one single time the Rabi frequency, you just need to make one transition to get another N in this harmonic oscillator. If you do one other pulse, you get another N. So you have a quantized way to increase the motion or to increase the occupation number of this harmonic oscillator. And this is what people use, is a very powerful tool. And once you put this in state, the cool part of this is that they have different frequency. So you don't only prepare the system that you want as a qubit, but also you can measure, because now frequency, we know how to measure. This gives you very low uncertainty. And if you need more and more precision, what you do is just you measure more periods, and you have a very good way to measure frequency. So you can make very good systems by working with the internal state plus the motional state of the eye. And this match very well the theory. So this, of course, people have done this multiple times, and it's actually quite simple to make this with one ion. So the problem that everything that I showed so far is one ion. What happens if you put 2 or 3 or 4 ions and so on in these traps? And that brings you this to the reason of this presentation, is that why you cannot build a quantum computer with trapped ions with 1,000 qubits. And this is, I bring just 2 issues here. The first one is the ion separation is N-dependent. So with one ion, the ion will sit in the center of the harmonic potential and is fine. Then you manipulate them with a laser beam that you focus and you concentrate, you align to that position. Now you load 2 ions. So if your initial beam is aligned to the trap center, which is here, now if you put 2 ions, it's not that anymore. Now you put 3 ions. Then you wonder that you can control the 3 ions, but if you load 4, the position is different. So basically you need to prepare your experiment and work for many, many days, let's say with the same number of ions. Otherwise you need to realign again. Then this is okay, but the second problem is that now you don't have a single ion anymore. If you have more ions, you have additional motion. And this is what we call sometimes the motion of the ring or the ion chain. And this can be, for example, for just 2 ions, you get these additional modes. So if they move together, you have the action mode, but then they can suddenly start moving separately. So one go to left, one other go to right, and so on. If you have 3 ions, you have 3 additional modes, and so on. So if you add more ions, you have more movements actually, and you need to stop this movement before starting your measurements. And what people have done to solve this? So the first one is not actually a big problem. People have designed different traps to avoid this different separation. So the idea is that you can do this kind of traps here, that's segmented traps. So basically you build harmonic potential, many harmonic potential instead of just one, and then you can control the separation. So once you align your laser beam, it stays there, you don't have to touch anymore. The other thing is that you can actually collect the ions fluorescence independently, also by doing these multi-array photodetectors or multi-array photomultipliers. This is fine. So people, along the years, they developed tools to circumvent this. And how about the other? The other actually is not a fundamental problem because people know how to do. The idea is that now you have this action, this movement that they can, the modes of the ion chain will be different for the number of the number of trapped ions. And the issue is that each one of these modes has a different frequency. And how you do this, how you cool, if you have only 3 ions, or say let's start with 2, then you have this 3 frequency in one direction, 3 frequency in the other direction. So you have 3 directions, 3 modes. So if they have different frequency, now you need to cool the mode. So you don't worry about this separation, this harmonic potential. But you just select one frequency, you hold your beam, and you cool that mode. Then you go to the next. Since the next is a different frequency, you just detune your frequency, hold again, it is going to call another one. So you keep going. In this case, 2 ions, then you have these 6 modes. You do this quickly, I would say. But the issue is that if you put 20 ions, now you have 60 modes. Then you start with the 60, and then you cool that one, then 59, so on. At the end of the 50 or the 10 ions that you cooled, maybe the first one that you cooled is already hot, so it's not worth anymore. And this takes very, very long. So then this actually is not, I would say, impossible. But all the papers that you see with more than 25 ions, 30 ions, they were made for one publication. So basically you work hard 6 months, you do this, all this, but you want to prove something. Of course, this is not a machine that you convince the theoreticians that, oh, just give me your code and I will run 20 ions with your protocol. So that's the issue. So then the very long cooling times makes it very difficult because this is actually good for demonstration, but will not be good for quantum computing. So you cannot do anything very, very useful with 30 ions if you spend 1 hour to cool them to get one measurement. So this is quite challenging. And that's the reason people start to do this networking. And I'm good, not only people from cold atoms think about this networking, because the idea is that how you can do entanglement or how you can connect different quantum machines. So for ions, people start this quite long time ago. And the idea is that is more or less representing this figure here. So instead of having one machine running 30 ions, 50 ions, that you spend a lot of technology to do this, so you can maybe do with 10 ions, 15 ions, or somehow about this, that you can do these very good results with this, and somehow connect this with another quantum computer. And this works for the same as, for example, for trapped neutral atoms. So if you have some issue, so basically, or the atomic clocks that Vanderlei asked before. So we need to invent ways, because sometimes some experiments with working with more atoms is quite challenging. And this is kind of cartoon version of this. There were people thinking about this for quite long, and more recently, people start to do this with chips. And the idea is that you create a single chip with different regions. And the idea is that you basically have a small city here. So you have ions that you can produce in one lane. Then if you need to put all together, you just combine them and do whatever you want, and then separate again if you need to cool. And I would say that there's a pioneer work about this. And this brings you this polarization qubits. It's a very similar idea. And this started with Chris Monroe in 2004. And the idea is that you can think about transmit the information or somehow. If you measure something here with your qubit, your quantum information can be transported or translated or transferred to some other place. And this is a demonstration that this can be done, for example, by using what they call flying qubits, with photons, which are polarization dependent. And the idea is that you can build zeros and ones from ions and couple them via entanglement to ones and zeros of photons. And the idea works like this. With many of these systems, we have some property that is called the fine structure. And if you have the fine structure, if the ion or the atom, neutral atom, is in this F state, if you apply a magnetic field, it also opens these F states in different MF states, which are magnetic sensitive states. But the thing about this is that you can do transfers between these MF states to the excited states by polarization light that's polarized. And the polarization is actually, the transition are polarization dependent. And this polarization, the good thing about this is if you force the transition here, for example, what they call spin up here, you put in the system in the excited states, when it decays, it might preserve this polarization. For example, if this polarization, if the ion here does not flip the state, or for example, if you go to MF0 to MF0, it means that the photon scatters by this atom is the same as the photon that you needed to make this transition. So basically, if you need the transition to increase the MF state, this is sigma polarized light. When it decays, if it goes to that state, it must emit that photon with that polarization. And the idea is that we know how to measure the ion position, or let's say the state of the ion. And now you have a way to measure the polarization of the photon. So the idea is that once the atom decays here, it has two different states. And this is basically, one is pi polarized, the other is sigma plus polarized. And this you can emit, you can measure these photons here by just separating them, right? And this is the schematic here, how this is shown. By a polarization beam split cube that you can find in any laboratory, you can separate these two polarizations. And by separating these, you start to counting this, and you start counting that, and they are independently. So this is actually what people sometimes called polarization qubit, because they have only two states. And in this experiment here, they show that once they detect one photon here, they immediately can measure the state of the ion and see which one of these states here. And with this, you can build the entanglement. So they measure the probabilities of finding the ion in one state versus the possibility to find the ions in the other state. So once you detect your photon, you can go there and measure which state is my ion now. And they made this correlation between the probability of finding, the probability of finding the ion, what they define with the up state, is perfectly or mostly perfect with the probability of finding the photon in the horizontal polarization. And if you do this in the opposite way, let's say what's the probability to find the up ion in the vertical polarized state, this is almost zero. And I explain this, of course, if you look at these numbers, say, oh, this is 0.97, is not that quite good. But this is actually because in this experiment, they had a lossy channel. So they measure more one, or the efficiency in measure one was better than the other. So they discussed in the paper that in principle, you can make perfect. And they made this here in other bases. This is what people call to prove that you have entanglement, you need to measure 4 bases of the Bell states. And they measure by repeating this experiment, measuring different polarizations. And this is actually a quite good way to prove that the experiment, the qubit, you can detect your qubit, but also if it emits a photon, you can also do another measurement which is not in physically the same space. And of course, this is it's one demonstration, and it still is not convincing that you can couple 2 quantum computers. And they made a very similar experiment a couple of years later, where you have 2 experiments now. And they made this entanglement by, with the same laser sources, instead of exciting one ion, they excited 2, but they were in 2 different machines. So the photon or the laser couples this ion here and transfer to the excited state, and the same laser couples this ion here, and they are different machines. So they again collect this in fibers, and they made these similar measurements, and they again prove that you can connect these two by using these photons. of course, then you might ask, okay, why this is not the problem that is problem solved and then move on? Because still, there are two fundamental reasons here. So first, you need to detect something here and measure something there. So if this is a communication path that you have different machines, this, of course, should be almost instantaneously, because otherwise you do an operation here that takes a few milliseconds, the other operation takes a few milliseconds, and then you transmit this information, and then at the end you have probably seconds. So then this is problem one. Problem two is that most of these ions here, they emit light in a wavelength that is lossy with these optical fibers. So if there's, even with 2 meters, if you have 200 something nanometers, 300 something nanometers, you will not get all photons here. So there's always some loss. And then that's why people are working more recently to extend this by means of wavelength conversions. So the idea is that instead of working with the wavelength of ions, the best one, and unfortunately we don't have probably one ion that immediately gives you this wavelength here that's 1.5 micrometers, that is the telecom. This wavelength here actually is the one that you lose less information in the fiber. So, and even this paper here where they show 50 kilometers, they were able to retrieve 20% of the information. So it's not all in 50 kilometers. Of course, this is, you might wonder, if I build a lab, I can put 10 or 20 different machines in the same room. I don't need 20 kilometers, but still you have this issue with the time, the communication. So you do the measurements, you do another measurement, you need to do this somehow comparing the measurements, so it still takes time. But the idea is that most or many people here are working on this, trying to convert the frequencies and be able to extend this longer. In this experiment, they were able to show already very similar way, but again, they measure the photon. Based on that measurement, they will check the ion position. So they don't do simultaneously. The idea is that upon the condition of measurement, you go there and measure the ion and do these two measurements and see if they are entangled. So this is more or less, I would say, the future of this. I hope you can understand why you don't ask experimentalists to put 50 ion or 100 ion. So, and just to close this presentation, so the bad news, I would say that even the state-of-the-art or the best computers these days cannot replace a classical computer. This is true. So you can do many things still in classical computers. Of course, there are some proof of concept that not everything you can do classically. But the good news is that we just started. So the quantum computers started maybe not many decades ago. So, and then we are still learning how to build these systems. We are still learning how to do this mathematics or the gates, and we have a lot of room to improvement. So thanks.
Thank you, Emilson. Questions?
Thank you very much. Nice talk. Concerning this view graph, we have just started. Can you maybe make a few remarks on what the status is?
The status you mean like in my case?
Yeah,
No,
in your case, exactly.
No, in my case, I need still to put things together. I am not finished the experiment yet. But I mean, overall...
But what is the status of your experiment? What is the status of your experiment?
Oh, I need to...
Can you say something, or is it...
No, I can say something. We built all the lasers, so now, a few months ago, I had a student join us. I have, basically, almost everything is built. So the trap is built already, or almost built, because everything is pieces. I just need to put everything together. I have the vacuum system. The parts are there. I need to do some steps on coating, because this is actually made of whatever if you choose titanium or whatever the things you choose to do the blades, they are not highly conductive. So you need to do a film of gold or whatever. This is what I'm working, and then put everything together. So it's probably 1 or 2 months to assembly. But I'm talking about this, we just started this because the field is new. So we don't have quantum computation for maybe, the first paper I think is 195, when Peter and Zoller say a receipt, let's say, this can be done, or the protocols can be done with trapped ions. So basically 20 years.
Hi, Emilson. Thank you so much for
Thanks.
the very nice talk. And I hope you can set up the experiment very soon in order to be able to collaborate even more. A few days ago, or last week, I don't know exactly, Quantinuum announced a new chip with, I guess, 96 or 95 qubits in trapped ion systems. Have you heard about that? And can you comment more about this?
No, I think I was in a conference that they proposed to do this, and I think this is kind of circuits, and they are doing this array of very small, like a small city, I think. So I don't know actually if they can control this almost 100 ions. I think they can do this operation. Let's say I can move the position, I can flip the spins, but I don't know if they can fully entangle this. Let's say 50 ions or 100 ions.
So perhaps I misunderstood the news, because I guess they were saying that they did already.
I think they did it. I don't know actually, because from companies it's actually hard to, because the market prices will rise if you say that. But it's more or less is a quantum computer. These days they have like 1,000 qubits. But the issue is that, for example, most of these, if you do a protocol, you need some of the ions for error correction sometimes. So this is not actually, you need to have, but you cannot do, like say, I cannot do all the operation with all them at once. So you probably need some of them for detecting or for error corrections and these things. That's not actually part of your main code. That might be the case. So I don't think I see something, let's say a protocol to solve some problem with 100 ions. Or
no,
something.
I know,
Yeah.
but the news says that they have a new architecture, so it's not exactly the ones you are building here. So I guess it's similar to the chip you showed us.
Yeah.
But they said they have full control of the system. They can connect everyone to everyone.
Yeah.
High fidelity, as good as the
Single
most
ones,
simple.
yeah.
So I understood that they had done that, but perhaps it's just announced they would do.
No,
I read the news
yeah.
again.
I agree. For example, like few years ago already, they had like 30 or 50,
Oh, yes.
more or less. So you can control 40, 50, but the thing is that I want a protocol that runs with 50. Can I do? Then it's a different question. Because, for example, even like Chris Monroe, the machine is able to do 40 or 50. Even like many years ago, Rainer Blatt already has a trap that with 50. But if you look the papers, it's always 20, more or less, 20. 30 is at most. You don't see this continuously doing simulation with 20. So, because it's pretty hard. So then that's the thing. You can build this, but to cool them, you have full control. But once you say, I want to put all of them in the ground state, do an operation, 10 different gates, one after one, then I don't think it's practical. So that's the point.
Thank you.
I don't see. Yeah, I have one question here.
Hi, Wilson. Very nice talk. So, based on your last statement that a quantum computer would never, I don't know, replace the classical version of this, would you say that, let's say, a commercial version of the quantum computer would be a combination, a mix of classical part and the quantum one?
I don't know. We have a lot of hope, I would say, in neutral atoms. This is actually what people are paying more attention these days, because it's basically the same. But I think people just start on that. I don't think that people will do a single device where they combine classical and quantum operation. This, I think, is one step back. But I think to connect them, we need somehow something classical. I think there's always this kind of problems, so people can demonstrate that you can trap or you can see them 100 or whatever, but controlling them independently, it's more complex. So then this is actually, it's not this same that for companies, if you do like one version of your trap that can trap like 10 ions more every year, you probably can show your stocks will go high. But then after years, people will need to be convinced that, for example, for quantum simulation, I need something useful. So I need to trust that if I go in my lab, if I buy some computers, I can run any protocol with high fidelity and I can trust that device. So I think in this case, it's probably maybe 10 years or 20 years up until we have a version that will work with 10 or 20 qubits.
Okay, I don't see further questions. So, Amilson, thank you very much for the nice talk. I think we can thank Amilson again. We end here this session. We have some lab tours for those interested. And we'll be back here at 6 for Vanderlei's public lecture. Okay, thank you very much.